Okay, so this is practice problem number 11 from the work and energy practice problems. We have an object resting on a smooth table that's attached to a horizontal spring with a spring constant of 450 newtons per meter. Okay, so we know the K value for the spring, 450 newtons per meter. Okay, the object is initially held at rest 12 centimeters beyond its equilibrium. Okay, so somebody's holding this 12 centimeters beyond this resting length of the spring. Okay, and then it's pulled to a position 18 centimeters beyond equilibrium. Okay, so it's pulled 0.06 more meters to some final location. And then again, it's held at rest. And you're supposed to calculate the work the spring does on the object between these two positions. So we know to do this algebraically, we know our work energy theorem says our work is going to equal our change in energy. And here we just have elastic potential energy that's changing. So we know it's going to be equal to our change in elastic potential energy. Okay, so writing that out, we know elastic potential energy is 1/2 kx squared. Okay, so to take the change, we take the final minus the initial energy, which would be 1/2 kx initial squared. Okay, plugging in our values, and we can actually kind of rearrange this. We can pull out a 1/2 k, and then we have xf squared minus xi squared, and then we can plug in our, I mean, you could have plugged it in right here. I like to kind of simplify things, though, as much as possible before plugging in numbers. So we have work equals 1/2 times 450, okay, newtons per meter. Because we're per meter, and you probably noticed this over here, I had converted these values given in centimeters into meters. Okay, so our final position from the resting position is 0.18 squared minus 0.12 squared. Okay, and when you plug this into a calculator, you get 4.05 joules. Okay, so that's the algebraic way to solve for the work. The question also asks us to do this graphically. So we're going to scroll down here, and then with a little bit of movie magic, we can have our graph appear for our force versus displacement, in this case x, the displacement of the spring from its resting position. We've talked about that the graph, well, we talked about this briefly in class. Actually, I'm going to use the white instead. That F equals the spring constant times x. So we know that the slope of this line here, F equals 450x. Okay, so our slope is 450 newtons per meter from our understanding of that a spring, the spring constant is basically the slope of that F versus displacement graph. Okay, so work, we also know, we're trying to find the work, right, graphically. Well, work is the area under a force versus displacement, or in this case, we're calling it x. So F versus x, or F versus d curve. Okay, here we just have a straight line, so we can easily find the area without calculus. We want to probably split this up into two and find the area here and add it to this area up here, and that will give us the total area under this line. Okay, so first, this area here is going to equal, well, we know that its height here of this rectangle is going to be 450 times 0.12. Okay, so that's going to be the height. And then the width, or the length, right? The length times the width here is 0.06. Okay. And then we're going to add to that, Okay, so that's the area of the bottom. And then let's add to that the area up here, okay, which is going to be plus 1/2. Okay, the height here of this part is going to be, well, we got to scroll over here. So, well, it'd be the difference between these 2 points, right? So this top point is going to be 0.18 times 450 minus 0.12 times, wow, this is long, times 450. Okay, so that's our height here. Okay, and we said 1/2 because we know it's a triangle. So we're gonna have to take this. That's our height, and then this we're gonna have. Wow, we got 3 brackets times 0.06. Okay, because that's the width of this triangle. Okay, and when you calculate that out, it is again gonna equal 4.05 joules. Okay, so we are able to do it graphically because we know what the graph looks like. Okay, the force of the spring over the displacement. So F versus X is going to be a straight line with a slope of 450. Okay, and then we can solve for the area by adding the area of this rectangle to the area of this triangle. And that's what we did with all these numbers. I maybe should have done it in variables first, but we have the area equal to this first part is our rectangle down here. And then this next part is our triangle at the top. Okay. And this is multiplied by 0.06. Okay, hopefully that was helpful.